Okay, so let's recall that we were discussing the importance of the optimization of pre-emphasis de-emphasis filtering in the general context. We are not specifically referring to the FM systems or angle modulation systems, although they are most predominantly used in angle modulation systems. However, the basic theory that we are doing for baseband systems can be more or less easily carried to the case of FM systems with some simple modifications, which we will probably have no time to discuss. So let us complete the discussion that we were carrying out yesterday, and you may recollect that we had come to a stage where we had written the expression for the output SNR as equal to, we have our block diagram that we are looking at. It consists of 3 blocks: the transmitter pre-emphasis filter, followed by the channel, which also adds noise. Channel has some transfer function at c omega, and at the receiver we have a de-emphasis filter. And we were looking at the signal to noise ratio at the output of the de-emphasis filter, and the expression that we had obtained for the output signal to noise ratio was this. I think this is the point at which we had left yesterday. Is that okay? And our problem that we want to solve is, we want to choose a pair of filters, pre-emphasis filters and de-emphasis filters. We want to choose a pair of these, a combination of these two. Of course, we know that this combination satisfies a certain constraint. What is the constraint? That the product of all these 3 transfer functions should be a constant, right? HP omega, HC omega and HT omega, right? But within that constraint, we want to choose these 2 filters so as to maximize the output signal to noise ratio, right? Keeping, there is another constraint, keeping the transmitted power a fixed value, to be a fixed value. So it's a constant, right? So as I said, in general, solution of such problems is carried out through using the calculus of variations, right? But for this case, it's easy to solve this problem by making use of a very simple, well-known inequality in mathematics called the Schwarz inequality. Familiar with Schwarz inequality? It doesn't matter, I'll just give it to you now. So to do that, what we do is we slightly rewrite this expression. I multiply and divide this expression with the transmitted power S sub t, right? So this will become G square S sub t, which is a constant value of course, into Sn omega d omega, right, divided by, so I have this denominator which I had earlier, and instead of writing S of t as the second term, let me substitute for S of t. What was S of t? Integral of Sn omega into Hp omega mod square d omega, right? So I get this into this. This is nothing but St. The transmitted power is the power of the signal which is coming out of the pre-emphasis filter. The input of the pre-emphasis filter has a power spectral density function Sm omega, right? So the power spectral density at the output will be Sm omega times Hp omega mod square, and the area under the power spectral density at the output is the total power that you are transmitting, right? The power spectrum is given by this product, and the total power that is being transmitted is the area under this power spectral density. Is that okay? All of you with me on this? So we want to maximize this, keeping St constant, right? Now to do that, if we can suppose we keep the numerator fixed, because numerator is, if you see, really g square is a constant, s sub t in any case you are keeping fixed, right. S sub omega is it's a property of the signal, right. So there is not much to it. It does not depend on h p omega, h t omega at all in literally, because you are keeping s t anyway constant, right, in that sense. However, so therefore what we can do is we can maximize this quantity by minimizing the denominator, right, in some sense. But let me I think don't jump to any conclusions, we will just see what that means. To do that, once again there is a very famous inequality called the Schwarz inequality, which we use to find out what is the minimum value of this product. We can say this product will always be greater than a certain number, right, and it will achieve its minimum value, this product will achieve a minimum value under certain conditions, right. That inequality tells us under what conditions that will happen, right. It is called the Schwarz inequality. Let me take a fresh page. So this is what it states. These two integrals Sn omega mod hp omega square d omega into Sn omega mod h d omega. Actually, ideally speaking, I should have been using different dummy variables to avoid the confusion, right. You could do that if you wish. If I am using omega here, you could use omega prime here, right, but it does not matter as long as you know the context, there should not be a problem. This product will always be greater than or equal to the mod square of this integral. What do in this new integral, I take the square root of both these terms, the square root of the term here, the square root of the term here, and multiply the two. So this becomes Sn omega square root of that into hp omega hd omega modulus of that, right, d omega, and take the square of the modulus of this integral. This is what the Schwarz inequality states. That is, if I have two integrals like this which are being multiplied, their product will always be greater than the value of this single integral, whose integrand is basically the square root, the multiplication of the square roots of these two integrands, modulus square of this integral. Right. So the modulus square of this integral will always be less than or equal to, if you separate them out into these two integrals. That is Schwarz inequality. And this is not a complete statement of the inequality. The complete statement is that this inequality sign will become an equality sign, these two will become equal under certain conditions, right, and that condition is that these two quantities that we are using in the two integrals, they are more or less the same except for a scaling factor, right. If they are scale version of each other, then this becomes an equality, right. So equality holds if this is some constant times, I am calling the constant, denoting the constant by k square, the other term, other integrand Sn omega into hd omega mod square. I am sure you had occasion to use Schwarz inequality somewhere or other in your maths courses, because it often keeps arising often in many applications. So it is not anything new, really new for you. Okay, so that is a condition under which this product is equal to this. So what does it mean? That means when this condition is satisfied, this product will have the least possible value which will be equal to this value, isn't it? If this condition is not satisfied, this product will be always greater than the number on the right hand side, and the smallest value of this product is the right hand side, and that smallest value will be achieved under this condition. Okay. So, that really solves our optimization problem. You are solving this optimization problem, you are trying to maximize this, and in the process we know that the maximizing condition is basically given by this, right. This ratio will be maximum when this denominator is minimum, this denominator will be minimum when this condition is satisfied, and that specifies our requirement. Is that okay? So, now we can solve for H p omega. To do that, you will also need this condition that H p omega into H c omega into H d omega modulus square is equal to G square, right. This is a constraint that we have on these filters. So, if you look at these two equations together and solve for H p omega, you can express, you want to eliminate H d omega, solve only for H p omega, right. So, you can do that using these two equations, and if very easy it is to check that your optimum value of H p omega, optimum function, the pre-emphasis filter should have a transfer function which is equal to g k times square root of S n omega upon S m omega upon mod of H c omega. Basically, using these two equations, I am eliminating H d omega and solving for H p omega, right. That is very easy, because you substitute for H d omega square from here, right. You will get H p omega, this entire expression will be in terms of H p omega mod square, which you can then solve for H p omega. Actually, H p omega will come in the denominator, it will become to the power 4, and then you take the square root of that, and that is why you get finally this expression. I have skipped one or two steps, very simple algebraic steps. Yes, please.
So this seems to be dimensionally incorrect.
Why? Why is it dimensionally incorrect?
So G has the dimensions of mod of H c omega, H omega.
No, I think it is okay. There is no problem on this. You can check it out and you can discuss it later. This is fine.
G has a dimension of H cube.
G has a dimension of H cube, right? This is a ratio, right? So, you will be left with H mod of H square, right? So, it is fine, dimensionally it is fine, I think, there is nothing wrong. Similarly, if you solve for H d omega, eliminate H p omega from these two equations, you can solve for H d omega, and that turns out to be G by k into S n omega upon S n omega upon mod of H c omega. All right. And you can also find out what will be the corresponding maximum value of the SNR by using that condition. I will not write that expression, but you can write it down, right? As an exercise, write the corresponding expression for the maximum value of the SNR. That is when this condition is satisfied, right? That's very trivial. So, I'll just skip that moment. Okay. I think I will end this discussion by looking at the physical significance of what these filters are doing. Okay. So, this is what the optimum pre-emphasis filter should be like. This is what the optimum de-emphasis filter should be like. And if you look at these expressions carefully, they will make a lot of intuitive sense. assume for our discussion that HC omega, the channel transfer function, is an ideal transfer function, right? That is, over the bandwidth of interest, this magnitude is equal to some constant, let's say equal to 1, right? So this goes out of our consideration for this discussion, right? So what are we saying? That the pre-emphasis filter should have a transfer function magnitude square which is proportional to the ratio of noise power spectrum to the signal power spectrum, right? So what does it mean? That means I must emphasize, basically this magnitude, this transfer function will have large values at those frequencies where the signal is relatively small, isn't it? Signal power is small compared to the noise power, right? Remember, noise is going to be added later in the channel, pre-emphasis being done at the transmitter. So knowing that the noise has certain distribution at certain frequencies which is significantly high, I must prepare the signal, ready the signal to take care of that. I must enhance the signal those frequencies where I can expect the noise to be large, so that I don't have a poor signal to noise ratio even in that situation. So I must boost up those frequencies at the transmitter where I expect a large amount of noise energy to be present. That part of the spectrum should be emphasized. That's what the pre-emphasis filter will try to do. So the optimum pre-emphasis filter has to do this. Similarly, at the receiver, I must do the other way around, right? The de-emphasis filter is proportional to the ratio of the message spectrum, power spectrum, to the noise power spectrum, right? We want to suppress the noise spectrum, right? So wherever the signal to noise ratio is good, whichever portion of the spectrum, you put more weightage to that portion of the spectrum. Wherever the signal to noise ratio is good, anyway you have lost some signal because of the poor SMR, you give less weightage to that portion of the spectrum, right? So you emphasize, rather de-emphasize the portion of the spectrum where the signal to noise ratio is poor, right? And because the constraint is satisfied, you will ensure that there is no distortion, right? Because the product of the three transfer functions is equal to 1, so there will be no distortion, right? So this is what the physical picture is.
So before the pre-emphasis filter, I have no idea about the noise which is going to be added afterwards.
So you have to have some idea. If you want to do the optimum design, you have to have some idea. For example, you may even the fact, even the knowledge that it is white Gaussian noise is also helpful, right? If it is white Gaussian noise, you know what it is, and if it is not Gaussian, if you know what it is, you can optimize further, right? You have to have some idea in order to use this theory, right? And there are ways of finding it out. So the physical significance I'll just summarize and then we'll move on. So let's say HP omega will boost frequency components where the signal is weak compared with noise. Right? And relatively suppress those where the signal is strong. HD omega will do the other way around. It does the opposite. Okay. But remember that the signal remains unchanged because your both HP omega and HD omega are together designed in such a manner that the product of the three transfer functions is constant. Right? Okay. Any questions? We will move on. Now, although I have carried out this discussion for the case of baseband systems only, extending this discussion to both AM as well as FM is possible. For AM it is almost trivial because all you are doing in AM is changing the frequency band. So your filters, if you want, you can make these filters as band pass filters wherever required, right? Or you can still keep the filters at the base band at the both transmitter and the receiver because you have done the demodulation in the process, and you have brought the signal back to the X-band. So because the AM only carries out a frequency translation, the theory really does not change at all. Theory remains the same, except for some very minor detail about which filters are, the channel will be a band pass channel here, right? But other than that fact, nothing else really changes, right? For the FM, things are a little more complicated, but it turns out that by giving very simple arguments, you more or less can reduce yourself to the same solution, right? So I will not go into those details. I like to leave that as a self-reading exercise, right? How to extend these ideas to the case of AM and FM. Primarily, they remain the same. But for FM, they are this concept of pre-emphasis and de-emphasis filtering is particularly important in view of the fact that we already discussed when we discussed in the context of tonal interference, for example, right? We discussed it in more detail, and in view of the fact that the threshold is likely to be there, so you like to make use of every avenue that is possible to make sure that you remain above the threshold value, right? So you optimize the performance to the extent that you can. So now also, if you remember, in the differentiation in the FM demodulation process, there is a differentiation that you effectively do at the demodulator, right? And that differentiation can enhance the noise. In fact, you use the noise power spectrum, if you remember, is a parabolic spectrum, right? So the noise, that noise spectrum gets enhanced towards the edges, and you can make use of this theory to use a de-emphasis and pre-emphasis set of filters, which will optimize the performance, right? So I'll leave those details for self-reading because of lack of time. So we move on to now a different set of modulation schemes. So far, all the modulation schemes that we discussed basically three types of really two types of modulation schemes, namely various kinds of amplitude modulation and various kinds of angle modulation or exponential modulation, right? In all these modulation schemes that we discussed, the carrier was a sinusoidal signal, right? Now we can have situations where we use non-sinusoidal signals, and one of the important kinds of non-sinusoidal signals which are used as carriers are pulses, right? Where pulses are used to carry the messages of interest. Of course, we are still in the domain of analog modulation, and pulses are absolutely basic to the transmission of digital information. I am not talking about digital transmission here or transmission of digital information here. I am still referring to transmission of analog information, right? Continuous signal, continuous in amplitude and continuous in time. Even for transmission of such signals, sometimes we use pulse modulation, pulses as carriers, and when we do that, we call the resulting modulation schemes as pulse modulation schemes. Okay. Now, in pulse modulation schemes, the first thing that we need to understand before we go into any pulse modulation scheme is the fact that your as I said, your carrier is this kind of a thing. Why should we do this? That's one question that will come in your mind. Why? Okay. No, it really is application dependent. Reduced noise? Not really, I mean, directly for that reason. Actually, let's look at it this way. Suppose you are measuring a lot of data somewhere, right? Maybe you are monitoring the conditions on the sea floor. Maybe you are monitoring the conditions somewhere else or in some plant, right, remotely. So you have a number of measurement devices, and these devices all have to pass on the information to some central station, right? So there are two ways of doing it. You collect each of these sensors that you have, these monitoring devices that you have, it generates electrical information and modulates a suitable carrier and carries out a frequency division multiplexing of all these informations and transmits it to the central station, right. It's more convenient in such situations because you don't need really a large number of carriers. It becomes, the equipment becomes unnecessarily complex there, right. It's much simpler, and it so happens that most of the time your measurement rate is not typically that high in many applications. It's quite okay if you measure the temperature at one time instant, then measure something else, maybe pressure, maybe something else, and so on and so forth, and then come back and measure the temperature again, right. In the meantime, the temperature won't have varied too much, right. So what you are really doing is you are measuring each quantity, passing on the information and coming back to the same quantity again, right. You're multiplexing a lot of information by transmitting each information in a small interval of time. So during this pulse interval, let's say you measure the value of that parameter, it's maybe you modify its amplitude and transmit a pulse of a certain amplitude, and after some time you come back to the same value, same parameter, you remeasure it, maybe the value has changed, so you represent it by a different amplitude, pulse of a different amplitude, and just transmit the amplitude again, right. And in between these two you have vacant time, you have time which is not occupied by this particular measurement, right. You could have a second set of pulses, right, measuring the second parameter, and that parameter is transmitted in these slots, right, and so on and so forth. You have, depending on how narrow is your pulse width that you can make, and how much time interval you have between two pulses, that is how frequently you have to transmit this information, you can multiplex in time domain many such informations one after another, right. So during this time interval, you're let's say you're looking at information in channel 1, during this time interval you're looking at information in channel 2, and so on and so forth. Your channels are now different time slots, right. So basic answer to why is that it offers me a simple way of multiplexing multiple messages on the same transmission medium, right. So it leads to time division multiplexing. So it provides me an alternative method of multiplexing information. One can also use frequency division multiplexing even in this context, but in many situations in this kind of a thing is much easier and much more convenient to do than frequency division multiplexing. Right? So that's the basic purpose. Implicit in this whole thing is the fact that even if you are, let's say you're looking at temperature, right? So the temperature has a certain profile, right, as a function of time, right? These are all time axes. Temperature has a certain profile. So it is implicit that you will not be able to transmit this continuous information now, right. At best what you will be doing is you are looking at this temperature information in this time interval, then looking at it in this time interval, and so on and so forth, right. So now you may say that you are losing information, you are not really getting all the information that you want, right. The answer is correct. In general, yes, but I am sure you know the sampling theorem. If that sampling theorem condition is satisfied by this signal, right, and if you sample this parameter at a sufficiently fast rate, you will not lose any information. You can reconstruct this entire waveform by just knowledge of the samples at specific time instance, right. So central to the theme of pulse modulation schemes is the sampling theorem, which all of you know, right. What does the sampling theorem state? The sampling theorem states that if a signal, if a message MT has a spectrum M of f which is limited in bandwidth, let's say to W hertz, right. So, sampling theorem is really for band limited signals. Its spectrum is from minus W to plus W. It has no spectral components above W. Then it is possible to reconstruct the continuous waveform MT from its samples taken at intervals of Ts seconds or taken at a rate of Fs samples per second, right. If you just have the samples of this signal at a rate of Fs samples per second, where F sub s is greater than 2W. If you choose a sampling rate to be greater than 2W, then it is possible to reconstruct MT from these samples, right. And what is the reconstruction process? You have to pass these samples through an ideal low pass filter, right. So, the operation is a low pass filter of bandwidth W. This is the summary of the sampling theorem. If you have forgotten it, quickly review it, because the entire pulse modulation scheme, this set is based on this result, the sampling theorem result, right. So, the mathematical description of the sample signal will be as follows. If I use impulse functions for sampling, to simplify, the simplest kind of sampling is if you were to, each of these pulses becomes an impulse, right. Mathematically, the entire treatment is very simple in that case. So, the sample signal when you use impulses for sampling will be given by this. These are the sample values m of n times Ts delta t minus nTs, right. So, the nth sample is associated with an impulse function located at time t equal to nTs, n going from minus infinity to plus infinity. So, this is called impulse sampling. Of course, it is not very practical. The first kind of modulation that we discuss is called pulse amplitude modulation. So, as you see, now everything else is the basic concepts are the same. You have a pulse strain which is your carrier, okay. Instead of a sinusoidal signal of some frequency, you have a pulse strain which is a carrier. So, you want to carry out a modulation, basically what does it mean? You want to embed the information that you want to convey on this carrier, right. Again, how can you do that? You can modify some parameter of the carrier in proportion to the information that you want to embed, right. So, you want to make either the amplitude proportional to the message signal at the various time instants. What are other parameters of a pulse? Width, pulse width is another parameter, right. You can make the width of the pulse proportional to the signal amplitude at that point. You can make the position of the pulse proportional to the signal amplitude at that time, right. These are the things you can vary. These are the three parameters, which is very similar to the things that we do in sinusoidal carriers. Modify the amplitude, gives you amplitude modulation. Modify the phase, that is like shift, so that is like phase modulation, is somewhat similar. Modify the width, that is like changing the frequency of the carrier in some sense. I am just giving analogy, it is not exactly the same thing. Okay. So, just like you have three parameters there with which you can play around, you can also play around with these three parameters and come up with three different kinds of pulse modulation schemes. Pulse amplitude modulation being the simplest. Pulse amplitude modulation is essentially sampling, right. So, the sample signal in this case is that is denoted by m sub ct. C denotes the carrier. Carrier is a pulse strain here, and that will be the same thing as this. into, instead of an impulse function, you have a rectangular pulse function, right, of the kind that I drew here, right. So, this is a notation for a rectangular function. Instead of writing RECT, sometimes we just use this notation to denote a rectangular function with some argument, and the argument is t minus NTS plus half tau upon tau. So, let me explain this notation. Pi t by tau is essentially this kind of a function. Right? This is a plot of pi t by tau, right? And this function, when it is shifted by this much, so basically you are taking these samples, you know, you are shifting this pulse to a general time instant NTS. Also, this pulses, because of this tau by 2, implies that you are shifting it, you are flushing it at time 0. So, the center of the pulse, the first pulse is not 0, but it is tau by 2, and so on and so forth. Can you tell me how I can get this kind of a signal from this kind of a signal? This is your impulse sample signal, right? How can I get a PM signal here? This is a PM signal. As you can see, the nth pulse, which is a rectangular pulse located at time NTS, has an amplitude proportional to the message value at that time instant, right? So, this is what we call a PM signal, right? Now, how can I obtain this signal from this signal? Basically, you have to go through a filter which converts this impulse into this rectangular pulse, isn't it? That is what you have to do. So, if I pass this signal, pass this impulse sample signal through a filter whose impulse response Ht looks like this, right? Then if I have m delta t here, I will get mct here, right? So, I can generate, of course, direct generation is much easier, but mathematically this is a good model, because this helps you to understand the nature of the PM signal, right. So, I am sure when you did your sampling theorem, you talked about impulse sampling, natural sampling and flat top sampling. What kind of sampling is PM? Flat top sampling, right. PM is essentially kind of flat top sampling, as you can see. You see, that is what the definition is. You are having a flat top pulse. This is a pulse that you are transmitting, whose amplitude is governed by the message value at that time instant, right. What happens in natural sampling? This pulse is not flat top. Its amplitude varies in proportion to the variation of the message in that time interval, right. But that is not what we call pulse amplitude modulation. Pulse amplitude modulation is basically flat top sampling, right. Now, if you do this kind of a sampling, what happens to the recovery process? How will you demodulate? So, the modulation process is really very simple. Modulation process is generating these pulses whose amplitudes are proportional to the message signal. So, to do demodulation, suppose you did, okay, there are two issues. Suppose I really had impulse sampling. I know what is the process of recovery. The process of recovery is one of ideal low pass filtering, right. That is the process of recovery. That is all. How will things change when I have this signal coming in rather than this signal coming in? Have I done some modification here? Yes, have multiplied the spectrum of this signal by the Fourier transform of this rectangular pulse, right. So, you will have to first modify, have a receiver filter which will have the inverse transfer function, right, which will cancel the effect of this pulse broadening that you have carried out, the holding, pulse holding, you have done a sample and hold kind of operation here, right. Of course, you are not holding till the next time instant, but till the next pulse, but you have done some kind of broadening of the impulse to a finite width pulse, right, and that modifies the spectrum. How does it modify the spectrum? So, before I discuss demodulation, suppose I ask you, what is how does MC omega differ from M delta omega, right? And answer is that there is a product of this with what is the Fourier transform of this same function, right? Of course, there will also be a phase function associated with this because it is not centered at 0. So, e to the power some j theta f, right, which at the moment I am ignoring, right. There will be some phase function associated with that because of the phase shift, because of the time shift in the time domain. More specifically, h of f actually will look like this, mod of h of f etc. And the phase function, I should take this as a reference, will look something like this. You can verify that, right. Etc. Remove this line. This will be the nature of theta of f. Okay. So, the important point is this, that the spectrum of the received signal is not just the message spectrum that you are looking for in your, it is getting modified by this shape here, right. Some kind of filtering is being done, right, by this filter h of t. So, you have to equalize for that, so that it is equivalent to coming back to your impulse sampling. So, the recovery or demodulation will be as follows. It will be actually a two-step process. In step 1, you pass the modulated signal through an equalization filter with transfer function, let us say h sub E f equal to 1 by h of f. So, mind you, this really will become unnecessary if your pulse width is very small, isn't it? Suppose if this pulse width is really very small, then this main lobe will have a very large width, right, and it will be more or less flat in the bandwidth of the message signal, right. So, in that case it will not be necessary, because, and that is intuitively it makes sense, because if the pulse width is very small, you are back to more or less impulse sampling, right. The pulse width is large, then this becomes important, equalization becomes important, right. So, unnecessary if tau is much less than Ts. And step 2 would be pass the resulting impulse sample signal through a low pass filter, through an ideal low pass filter. Okay. Any questions here? So that is all there is to pulse amplitude modulation. Pulse amplitude modulation in summary is essentially flat top sampling, right. So just like you recover the signal for a flat top sampling case, you are doing the same thing here, nothing more than that. You in a flat top sampling case, you do require an equalizer followed by an ideal low pass filter. Of course, this requirement of ideal low pass filter can be a little stringent, right, because you can't physically realize ideal low pass filters. So typically this is handled by, how do you handle this situation? That the fact is that your low pass filters will not be really ideal. So in practice, how will you handle this situation? Your sampling rate should be somewhat larger than 2W, right. Remember what, because I have not gone into the details of the sampling theorem here. I am assuming that all of you know the reason why you require an ideal low pass filter, right. The ideal low pass filter comes because your sample signal has a replicated spectrum. The spectrum of the sample signal replicates at intervals of 1 by Ts. It's a periodic spectrum, and when you want to reconstruct continuous time signal back, you want to keep only the central portion of the spectrum, removing all the other repeated portions of the spectrum, which can only be done by ideal low pass filter. If however you make sure that the replicated components are well separated from the desired component, then you have a slightly better situation in terms of design of your low pass filter, right. Let me just recap for you if you are not recollecting. Suppose your message signal has this kind of a spectrum, right, and the sample signal has this kind of a spectrum. It goes up to infinity like that, extends up to infinity both sides, right. So if you want to reconstruct this signal back, you have to pass it through a low pass filter. If you have sufficient gap between these, then you have a possibility that instead of working with an ideal low pass filter, you can work with a slightly non-ideal filter, right. Basically that is what. So if the situation where you have difficulty in designing ideal low pass filters is typically handled by making sure that the sampling rate is somewhat larger than 2W, because this is centered at Fs. So this will be Fs minus W, right. You don't want this point and these two points to be close to each other. There should be a guard band, right. If you have a sufficient guard band, that guard band provides for designing more practical filters rather than an ideal low pass filter. That is one thing. The second thing is, if you do not provide for guard band, a certain kind of distortion occurs, which we call the aliasing distortion, because this lobe will now get merged with this main lobe and you will not be able to separate the two out. When you do a low pass filtering, some portion of the spectrum from the next lobe will also interfere with the main lobe, and your resulting reconstructed signal would be a distorted version of the original signal and not what you. But these are things that you already discussed in your sampling theorem, so I am not going into details of those. So that is as far as pulse amplitude modulation goes. Any questions on that? So we quickly come to, okay, we will stop here. We will discuss the other two kinds of modulations, pulse width and pulse position modulation next time. Thank you very much.